The world is changing and climate change is inevitable. As a result of climate change, the number of disasters are also increasing. Floods are no exception. Floods have a huge impact on the daily lives of people, which is why addressing this issue is of vital importance. What if you had a tool that could tell you which are the safe areas that you can go to during a flood? It could guide you to the rescue team and rescue centers. It could guide you to areas that can provide you with life saving amenities such as food and shelter. That is the kind of tool that we are aiming to build. Hello everyone, we are Team Hydrocode and our problem statement is projection of the extent of inundation corresponding to the forecast of flood levels in a river. We will be predicting the spatial extent of water flow that happens during a flood using the concepts of interpolation and extrapolation. With the help of this prediction, the rescue team will be able to carry out its operations efficiently. What are the features that we are aiming to achieve? We will be taking care of pre-disaster, during the disaster, and post-disaster. So we'll have an early warning system that can tell you that a flood is going to come or what is the kind of damage that the flood can cause, what is the kind of water flow that the flood will have. We'll also have a real-time monitoring system that can tell you which are the areas that are affected the most, which are the red zones, which are the blue zones. We'll also have flood risk assessment. That is, after the flood has happened, we will be analyzing the flood with the help of which we will be able to do better predictions in the future. We'll also have efficient rescue team management. We will be able to convey to the rescue team which are the areas that have a large number of people trapped because of the flood, which are the areas that needs to be taken high priority for. The users will also be able to use the interactive map interface. The users will be able to interact with the area, that is, they'll know what is the area when the flood water is in that level, and what is the area when the flood water is lesser. They'll be able to figure out the area's topography and they'll be able to navigate in an efficient manner to reach the rescue team quickly. So what is our idea and approach to this? We'll have precision imaging, that is, we'll be able to convert imageries into high resolution DEMs and SAR images to be processed by the GIS application. So DEMs are digital elevation models, they're representations of the Earth's surface, and SAR is used to create two-dimensional and three-dimensional reconstructions of objects. GIS is a powerful tool for capturing, storing, analyzing, and visualizing geographic data. So we'll also harness a synergy of diverse data and use machine learning and HEC-HMS to craft a predictive hydrological model that anticipates water flow and accumulation. HEC-HMS is a numerical model that is designed to stimulate the precipitation runoff. It is applicable in a wide range of geographic areas and solves a wide range of problems related to hydrology. So we'll also deploy hydrological predictions into HEC-RAS for a reliable hydraulic model. So with the help of this, a detailed visualization of flood impacts is obtained using the concepts of interpolation and extrapolation. Interpolation is a statistical method used to estimate an unknown value or a set of values. And extrapolation is extending a trend or pattern that has been identified with a set of existing data points. So what is interpolation? If I have data for 12 feet and 15 feet, I will be able to predict what would happen for 13 point feet. That is interpolation, that is thinking in between. Extrapolation is if I have data for 12 feet and 15 feet, I'll be able to predict what will happen for 18 feet. That is thinking beyond, and that is extrapolation. We'll be including robust features such as optimizing rescue paths, timely alerts, classifying high risk zones, and guiding people to rescue centers, ensuring reliable actions during crucial moments, etc. Our architecture is a full stack app along with front end, web app, and back end. We will also be using cloud, and along with that, we'll be including AI ML models such as ANN and random forests. We'll also have hydraulic and hydrology models. So, what is hydraulic and hydrology models? A hydrology model is a mathematical representation of the processes that govern the movement of water in the Earth's environment. And hydraulic models focus on the behavior of water in rivers, channels, and floodplains. HECRAS are examples of hydraulic modeling software. We require data, so we'll require climate data, meteorological data, topographical data, past flood data, and dam level data. So that's it about the architecture. What are our use cases? We'll have predictive analysis. We'll be able to forecast flood zones with the help of interpolation and extrapolation. We'll be enabling alerts, SOS. We'll be able to connect people with rescue teams and centers. We'll also identify potential damage areas and vital infrastructure threats. We can observe that during floods, what happens is the buildings get affected, infrastructure gets affected, and all of these will fall on the people, which is why they may lead to loss of lives. This is more uh, dangerous, and which is why we need to assess what would happen during infrastructure also, insights also. Operational visualization will be streamlining relief efforts with flood overlays. We'll be able to provide localized analysis and list potential rescue centers. What are our dependencies? Our dependencies are data collection is difficult as all the required data is not available in a single place. And network should be reliable for most of the features to be available. So we'll have two network modes, that is a low network mode and a high network mode. So in the low network mode, our app will function with minimal abilities, will have minimal amount of features, and in the normal network mode, our app will have all of the features available. We can observe that during floods, the network is not that great, which is why it is difficult for us to implement all the features in low network mode. But we do have an app that can take care of the minimal requirements, providing minimal information and information to lead to the rescue centers. This would function even when there's low network. Our data will vary from region to region, which is why each region may have its own unique challenges. We may not be able to address all the challenges of every area because we'll be following a generalized approach. So, we may have unique challenges during this process. Our technology stack is as follows. We'll have GIS, MLDL, hydrologic and hydraulic models, and full stack. So GIS is used for map visualization. MLDL include ANN and random forests, which are popular machine learning models. As I've already explained, hydrologic and hydraulic models, HECRAS, HECHMS are also being used. And our full stack will be using React.js, Django, PostgreSQL, and AWS. What are our showstoppers and major features that we want to implement? We'll have 3D flood tours. We'll be able to create 3D models that lets users explore floods in real time or from the past. It's like taking a virtual tour of the flood zone. We'll have traffic hacks, that is, we'll be mixing live traffic info with flood data, helping rescue teams find the quickest routes, avoiding flooded streets and traffic jams. We'll stay safe with geofencing. That is, we'll be able to get alerts when you wander into flood zones. Your phone basically becomes your personal flood alarm. We'll also have smart evacuation. That is, the app figures out the best escape routes on the fly, considering traffic, flood levels, and where we want to go. We'll also have an offline or a low network mode, like I already mentioned. We can say that we have built 1D and 2D models up to now, and we have integrated with the front end and back end. We'll also be using ML models like HECRAS and HECHMS, and we also have an option to reach out or call to the rescue team operation, and this is in implementation, and only the last stage of execution is remaining. This is our team. I am the team leader Ananya, and we have Bharat, Haricharan, Aditya, Advait, and Harish in our team. That's it for the presentation. Thank you.
First, we'll see the flood prediction model during the pre-disaster moments. As we can see here, we have used the data set, and after pre-processing everything, we are going to using sklearn to develop the ML model. First, we are going to predict whether the flood will happen or not. This is during the pre-disaster moments that will help us to efficiently run our code, and it will not run on the cloud 24/7, and we'll know that when the disaster is going to happen, and then we're going to find the output of this and predict the hydrological model. Then we'll feed into the hydraulic model, which will simulate the flow of the river and where it will go and damage places. As we can see here, we have trained our model using KNN classifier and using other 5 models. As you can see, we also use decision tree, random forest classifier, And comparing the final accuracy of our models, we are finding that linear regression gives us the most optimal output. After predicting whether the flood will occur or not, now we'll predict the severity of the flood. Going through the same pre-processing, we are using logistic regression model as you can see here, and we are getting the accuracy scores here. Now, using logistic regression, we are going to get values as 0 or 1. 0 being there is no chance for severe flood, and 1 being a chance for severe flood. Now we are going to use random classifier in the middle so that we can find the range in which the severe flood is going to occur. Here we can see this middle values correspond to the water gauge levels that forms the hydrological model, which we are going to feed into the hydraulic model that is being powered by HECRAS. HECRAS will simulate the hydraulic model, and then it will give the output as where the flood is going to flow and how much depth it is. And now when we are feeding it to the HECRAS model, it will show the extent of flood inundation, the watershed delineation, and the extremities of the boundary area where the flood is going to happen. For our prototype, we need dataset from two major websites. First is the spatialreference.org, where we give the zone in which our river lies. For us, it's India Zone 2B. Press search, and as we can see here, there are three datasets available with us: Kalyanpur 1937, 1705, and 1880. Let me select the latest one and click the .prj file. .prj file is the one which has all the information regarding the coordinates, the contour lines, the spatial reference lines, and all other profile lines. Let me give save. And the second is the .daf file or .dem file that is required for us, which contains the data of the river elevation and degradation. Go to Bhuvan National Hydrology Project website, click the Open Data Archive, select the satellite from which you need your dataset. For us now it's ResoSat1. Select the option tiles. Start selecting your tiles. Since my dataset lies in this region, let me select it and give next. Now this file has .dem extension. As we can see in this metadata, we can also see the coordinates where they have been held, and this is the geotiff.daf format, which has the data related to the river's elevation, the river flow, and all of this. As we can see here, if we give a view, we can see the thumbnail view, which represents, see here, the red lines indicate that the level is high, and the green indicates that the level is low. We can see the branches branching here, which looks like a tree, but it actually is a river. We are selecting a river called Panchayat River in Jharkhand, which is being neighboring West Bengal. So we are going to select Zone 2B for our projection selection. Here, as you can see, the spatialreference.org, we have to input India 2B. So here we can see that there are various data sets from various years, and since we need the most recent one, we are going to select Kalyanpur 1975, India Zone 2P. And you have to know this value EPSG2430, which will be useful for later. Here there are many types of files, and you have to click for this .prj file and download a projection file. That's it for the data set. And now let me show you. First, we'll see the 1D modeling of a river, that is how a river flows when there is no flood. Now, as we can see, now we'll see the 2D modeling. The simulation. We are doing the simulation in an application called HECRAS, which is specialized to simulate the flow of river in an unsteady manner and a steady manner, which is called steady flow and unsteady flow. Here, I'm going to present you what happens, how the flood inundates when the rainfall pours over a long period of time. So, since this is an unprecedented event, we don't know when the rain is going to happen, and it happens suddenly. The water flow will not be steady at all. So, we have to select the unsteady flow part. I've already created the project, so let me open it. We can see here I have completed the geometry, unsteady flow simulation, the plan, and the project. Here we can see that I have included the flow hydrograph, precipitation values. These precipitation values and can also be got from our Indian website, which I have shown earlier. These are all the precipitation values on 2nd March 2020 from time 00 to 19 hours. And here we can see the data of up to 7th March And I have now given the influence. Now we can see, we can plot the data and then see how the rainfall is happening. I have smoothened out the edges to show a proper rainfall and simulate how the water is going to flow over a steady period of time. So as we can see, the waterfall is increasing steadily, the precipitation is increasing steadily, and then we can see the normal depth. Normal depth I've kept it as 0.01. Now, so as to show that the normal level of the river which is being flowing is 0.01. And now I will show you later that when we mark it on the map, we are going to see the elevation level compared to 0.01. If it is 0.94, it is which is far greater than the original level set by us, and thus will indicate there is a flood there. Now we are going to see, we have not included sediment, and we have simulated it for 1 minute intervals. As you can see, the software takes some time to load because it's simulating all the process that has been happening. So yes, let me first zoom out and show you that this is Indian Jharkhand West Bengal, and the Damodar perimeter that set. As you can see, this is Jharkhand West Bengal border, and this is the Panchayat River Dam, and the Damodar River flows from this dam to West Bengal. Now I'm going to show you the depth and the geometry. You can see that I have marked the boundaries here, which shows that until which area we are calculating the flow catchment. And this line, which is known as the break lines, show that the flow of the river direction. This is for the reservoir, and this grids will enable us to simulate the flow of water in all over the place. Now, after collecting this depth, we can set the opacity to our liking, and then we can start simulating it. Initially, since we have set the river value to 0.01, we can see that here that the river is steady. There is no overflow catchment. Since we have decreased opacity, we are not going to initially see the flow of river in dark blue colors. Let me turn off the geometry so that you can have a better visualization. After the initial start of raining, which is precipitation, we can see that the water level is being slowly increasing in the areas which have low depth. And here we can know the time in which this is being increased. So I have selected the range between 3 March 2020 from 12 o'clock to 1 o'clock. So as you can see, we have given the values for precipitation values from 12 o'clock till the next day 12 o'clock. So we are selecting a time interval in which we want to say the flood inundation. And as we can see, in the past hour itself, it has been elevated so much. And in our previous discussion, we would have seen that we are going to have a low power battery mode and low net connectivity mode, and I'll explain how it is going to happen. If you have noticed it before, I would have said that the initial level of the water is 0.01, and compared to 0.01, now it is increased to 2.10 value. What is 2.10 value indicates that the flood has increased almost 2 times of its original height, and this means it has increased more than 1 times of the original height. So we are going to send this 1.47 or 1.30 value along with the coordinates to our end system application. Which what we'll do is, since these are just numbers, it will take low amount of kilobytes, and it can be happen over a low range of low bandwidth and low net connectivity. So what will happen is these coordinates will go into the map, and this will be plotted alongside the river. So even without simulating all of this application in the end user's mobile phone, we can just simulate it in the cloud, and we can just send the values so that it will be easy for them to rescue and navigate the process, and it will be more smoother. Now we'll see the prototype of our website. First is flood drainage forecast. We can see the flood that is being drainaged and damaging all the places. We can see it on any map that we want, any area that we want, and any date that we want. If we select a future date, it's going to extrapolate and predict how much the level will rise or decrease. But if we select a past date, it will show the previous records of how much the flood has affected those areas. Next, we'll see the shortest route, which will show us the actual shortest route is from 1 to 2 is this, but since it's being affected by flood, we cannot access this route. So it's taking a detour and finding the shortest path that is available to us in the face of a crisis. We can say that here is a bridge and the flood level is relatively low here as compared to here, which is high. So it's optimally choosing a path that is easy for us. We can also select whatever map we want, any type of area we want, and any date that we want. Next, we'll go to the data analysis of floods. We can see the past, present, and the future data in forms of graphs, which will tell us two legends. Is the flood serious or it is an mild amount? As you can see here, since the flood data represented as 25 centimeters, it's not that much of a flood, so it's not shown in any vibrant colors like red. But if it is above 300 centimeters, we are going to use the legend and show it as in red, orange, or some other color. As same as those, we can see any date and in any place. The graph description and location all can also be changed. These are all the sections that we have done, and in the future, well, in the next one, we are going to complete the prototype for request for help, chat with rescue team, and the interface for all the personnel who is going to be involved in rescuing of people. Thank you.